So what is increasing and decreasing functions? A function f is strictly increasing on the interval if x2 greater than x1 implies fx2 greater than fx1. Basically means if x increase, your y value also needs to increase. That is an increasing function. A function is decreasing, which means your x increase, but the y value is actually decreased. That's a decreasing function. But one thing you need to pay attention is, if I have a graph like this, okay, we have this point, wait. Let's say we have the shape like that. Okay, we have the shape like that. And I have this point is -1 and 4, and this point is -4 and -1. Okay, which part of the graph is strictly increasing? Okay, just this is the example. Okay, where is strictly increasing? So strictly increasing is -infinity to the point -1, but include the -1, union the point 4 to infinity. And where is strictly decreasing? It is from -1 to 4. Okay, it's including both turning point. Okay, it's include both turning point. So the thing is, you must have square brackets at the turning point. Okay, so the word strictly refers to the use of strict inequality sign, small or greater, rather than small or equals to or greater equals to. So, okay, I will say a function f is increasing. I'm not saying strictly increasing. I'm just saying a function f is increasing on an interval if x2 greater than x1 implies fx2 greater or equals to fx1. Okay, that's the difference between increasing and strictly increasing. Okay, I can use greater or equals to for increasing without the word strictly. So let's have a look at this diagram here. Okay, we have a linear and we have a horizontal line here. Okay, linear and horizontal line here. That point is 2, 5. Okay, this function is strictly increased. Strictly increasing. Okay, what is strictly increasing? Strictly increasing is from -infinity to this 2. But if I just say increasing function, if it's increasing in R. Okay, your x2 greater than x1. If it's increasing, it only needs to know that the y value is not decreasing. It can be the same. Okay, it can be the same. It just implies not decreasing. Okay, my x increased, but I want the y value not decreased. So, which means this horizontal line, okay, when x increased, the y value remain the same, but it's not decreased. I can say it's an increasing function, but it's not a strictly increasing function. Okay, it's not strictly increasing. I can say it's increasing, but not strictly increasing. Okay, that's the difference between strictly increasing and increasing function. And same thing happens for decreasing and strictly decreasing function. So a horizontal line can say it's an increasing function, or I can say it's a decreasing function, because the value is not decreased or not increased. So I can say it's either increasing or decreasing. Okay, so this horizontal part is increasing or decreasing function. Okay, if f dash x greater than 0 for all the x in the intervals, then the function is strictly increasing. If f dash x smaller than 0 for all the x in the interval, the function is strictly decreasing. Warning. The function fx equals to x cubed is strictly increasing, right? Look at the graph, that's x cubed. The graph is strictly increasing. But at the point 0, you have f dash x equals to 0. F dash 0 equals to 0. This means that strictly increasing does not imply x dash x equals to 0. So which the sentence means, if you work out your f dash x equals to 0, you cannot tell anything about this point. You cannot say it's increasing function or decreasing function or like not decreasing, not increasing. You don't know anything. You need to see the graph and tell me whether that point is strictly increasing or decreasing or not increase, not decrease. You can't know anything. But if you know f dash x greater than 0, it must be a strictly increasing function. If you know f dash x smaller than 0, you know it must be a decreasing function. But when you have f dash x equals to 0, you can't say anything about it. Okay, you can't say anything about it. For example, just the point here. You solve out f dash 0 equals to 0. Can you say at the point 0 it's not increasing or not decreasing? No, it's strictly increasing at that point. Okay, so you need to see the graph and test about that. Okay, let's have a look at this one. The graph f dash x. Okay, the graph of f dash x. Given a graph fx, so this is the fx graph. We can sketch the f dash x graph. Okay, we can sketch it roughly. Okay, we can sketch it roughly. We can't sketch a particular one for sure, but we can sketch it roughly. Okay, first of all, let's see, we have a cubic here. Okay, we have a cubic graph here. We have a cubic graph here. So, what's the derivative should be? What type of function the derivative should be? Parabola. So, we have 2x intercept. So let's see where's the turning point. The turning point is here. Okay, the turning point is here. We have the turning point here. So at this turning point, I should have x-intercept for sure. Okay, we should have x-intercept for sure. And we have here. Okay, that's the turning point. So I should have x-intercept here as well. Okay, so we have x-intercept here. The next thing is we can have increased small face or the set face of the parabola. I can have this shape, or I can have this shape. So how can we know whether it's this shape or the other way? So we look at in between this point and this point. Okay, in between those 2 points, the function is decreasing function. So I should have negative value. It should be below the curve. Okay, below the x-axis. It's decreasing in between those 2 points. So the derivative graph should be below the x-axis. Then the other 2 part is increasing function. So it should be above the x-axis. Then therefore, the graph should look like this. Okay, the graph should look like that. So this red one should be the f dash x. Okay, the graph should be f dash x. Okay, hint. The graph of the derivative function is 1 degree less than the original function, as you see from the rule of differentiation. Again, x to the power of n. Yeah. You don't need to really worry about that. You just show there's a turning point and it doesn't really matter where it turns. The important thing is just the x-intercept and the shape. 2 things, intercept and the shape. Okay, so quadratic will become cubic, cubic will become quadratic, quadratic will become linear, and linear become constant. And what constant will become to? what constant become 2? 0, y equals to 0. Okay, if it's a constant, you have y equals to 0. Okay, so that I think you know all of that. Let's just look at this example. Okay, let's just look at this example. Example 1. Okay, for example 1, what's this equation? What's this equation? What's the gradient for this equation? 0. It's a horizontal, y equals to 3, something like that. So when you derive that, you will have 0. Okay, you have y equals to 0. That should be f dash x. That should be f dash x. Okay, let's look at part B. What's the gradient for part B? Okay, so you have 0, 1, and you have negative a half and 0. y1 minus y2, you have 1. x2 minus x1, you have a half. So that gives you 2. So the gradient is 2. You will have a horizontal line here. Y equals to 2. Okay, that's a quadratic. What's the derivative should be? What do you have? Straight line. Where is the x-intercept? 2, 0. Okay, so I just interested in this point, 2, 0. But I can have two directions of the straight line, increasing or decreasing. Is that increasing linear or decreasing linear? Should my linear look like this or should look like this? Increase or decrease? Increase. Okay, increase. Why is increase? Because to the right of the point 2 is an increasing function. So the graph should be at the top. And then to the left, it should be below here. So you will have a straight line like this. But it can have different gradient for that point. It can be lower or higher. You just need to show that's an increasing linear. Okay? You don't need to worry about the gradient. You just need to know the x-intercept and it's an increasing linear. That point is 2, 0. Let's have a look at part D. Part D, I should have a quadratic, right? I should have a quadratic. And the turning point should be at -1. And the other turning point should be at 2. Is that a positive quadratic or negative quadratic? Positive, because in between -1 and 2 is decreasing, so it's below the graph. So it's a positive. This quadratic looks very bad. Okay, that looks better. So you will have 2, 0 and -1, 0. That's the point it needs to label. Okay, next one. Next one is a cubic function, and that's got a stationary point of inflection at the point 1, 0. So I will have x-intercept at 1, 0 as well. But do I have another x-intercept? Is there another x-intercept? No. Okay, then what's the graph will look like? Touches. What's wrong today? I just can't sketch properly. Well, that's 1, 0. Because both, like, it's all increasing graph, okay? It's all increasing graph. The whole graph is increasing. So all the gradient function needs to be above the x-axis. And I know I have x-intercept at 1, 0. So therefore, that's my graph. Okay, that's my graph. Okay, the next one. Well, I don't know what's the next one. I think next one is a quartic graph. Maybe it's a quartic. I don't really care. What I care is I have -1, 0, and I have 1, 0. Are the two intercepts? Okay, to the right of 1, I will have positive graph. Okay, I have graph here. In between -1 and 1 is still positive graph. So I have graph here as well. And then to the left of -1, I have minus. I should have graph below here. Okay, then what's the graph looks like? You have positive graph, positive, and you have below minus. Okay, the graph looks like that. Okay, the graph looks like that. That's 1, 0. That's -1, 0. In between 0, not in between. To the right hand side of -1 is all greater than 0. Okay, all increasing. To the left of -1 is decreasing, so it's below the x-axis. Okay, next page, example 2. Find the coordinates of the points on the curve with this equation at which the tangent line makes an angle of 45 degrees with the positive direction of the x-axis. So make a 45 degree of the positive direction. So what's the gradient? 1. Okay, so gradient equals to tangent 45, which gives you 1. So because the gradient equals to 1, I need to work out what is dy dx. dy dx gives me 2x minus 7. And then if dy dx equals to 1, my x should be 8/2, which is 4. When x equals to 4, I need to work out the coordinates, so I need to worry about the y value as well. So it's 4 squared minus 7 times 4 plus 8. 16 minus 28 plus 8, that gives you minus 4. So the coordinates will be 4 and minus 4. B. The tangent is parallel to the line y equals to minus 2x plus 6. Okay, it's parallel to that. Therefore, the gradient will be the same as that gradient, which is -2. Then 2x minus 7 equals to minus 2. 2x equals to 5. X equals to 5/2. Y equals to 5/2 squared minus 7 times 5/2 plus 8. 25/4 minus 70/4 plus 32/4. That gives you 57. 57 minus 70 equals to -13. So it's -13/4 That is 5/2, comma, -13/4. Example 3. The planned path for a flying saucer leaving a planet is defined by this equation. For x greater than 0, the units are kilometers. Find the direction of the motion when the x value is 2 and 3. Okay, so what is the direction of motion? What does that mean by the direction of motion? Yeah, to which direction is actually like flying or like it's moving. So if I have, okay, let's say if I have the path looks like this. Okay, if the path looks like this, then the direction of motion for any single point will be the tangent to that point. Okay, the direction of motion at that particular moment is the tangent to that point. Okay, so if the moving path is that, okay, if the moving path is that, the direction of motion at any single point will be the tangent of that point. So it's asking to find the direction of the motion when x value is 2. So basically what I need to look at is dy dx, which gives me x to the power of 3 plus 2x squared. Okay, for 2x squared when x greater than 0. Okay, when x equals to 2, dy dx equals to 2 cubed plus 2 times 2 squared. That gives me 8 plus 8, which is 16. Okay, what's the 16 means? The 16 means the tangent at that point is 16. So tangent theta will be 16. Okay, tangent theta will be 16. Theta will equals to tangent inverse of 16. Let's have a look at what's that. So what is tangent inverse of 16? That gives you the radian. Okay, it's in the radius form, so it gives you the radian. The radian is 1.5. Okay, the radian is 1.5. So what I can do, I can times this by 180. 180 divided by pi. That will change it to a degree form, which is 86.4. Okay, about 86.4. So that equals to 86.4 degrees. So the direction of the motion is made up with the horizontal x-axis with an angle 86.4 degrees. Okay, it's moving that direction. So same thing for the next part, which is when x equals to 3. Dy dx equals to 3 cubed plus 2 times 3 squared, 27 plus 18, which gives you 45. Okay, 45 is the tangent theta, okay? Tangent theta equals to 45. Theta equals to tangent inverse of 45. and I will times this by 180 over pi. That gives me 88.7 degrees. So the direction of motion is 88.7 degrees with the positive x-axis. Okay, with the positive, so I can say it's the ground. Okay, positive level of the ground. Make an angle with 88.7 degrees. Okay, next one. B. Find a point on the flying sauce path where the path is inclined 45 degrees to the positive x-axis, which 45 degrees means the gradient is equals to 1 already. So you just need your dy dx equals to 1. Okay, so I want to solve for a cubic. Equals to 0. Okay, so what I can do is factorize this. Okay, remember how do we factorize? We have 1, 2, 0, and negative 1. I can try negative 1. It gives me 1, 1, negative 1, and 0. That one worked, which is good. So I can factorize this as x plus 1, x squared plus x minus 1 equals to 0. I can keep factorize. That discriminant gives me 1 plus 5. 1 plus 4, which is 5, is greater than 0. So I can keep factorize. X squared plus x plus a quarter minus a quarter minus 1 equals to 0. X plus 1 will give me x plus 1 on 2 squared minus 5 on 4. So I can say that's 5 over 2 squared equals to 0. X plus 1, x plus a half plus root 5 over 2, x plus a half minus root 5 over 2 equals to 0. So x will be minus 1, x will be minus a half minus root 5 over 2, and x will be root 5 over 2 minus a half. Because your x must be greater than 0, therefore x can only be root 5 over 2 minus 1. Okay, you only have one answer here. You can only solve one solution here. Okay, this is a pretty good question. It's combine of polynomials and also combine differentiation together. Okay, you should be able to solve x cubed plus 2x squared equals to 1. So how we can solve for that? That's part B. Part C, are there any other points on the path which satisfy the situation described in part B? No other points. Because I have solved, like, for all the x, solve the gradient equals to 1. I solve out 3 points, but 2 of them is the negative value, only 1 is the positive value. And you can only take the positive side, so there's no other points which will satisfy this. Any questions so far? The domain is greater than 0. I solve for the whole function and I can solve out 3 points which can give you gradient equals to 1, but 2 of them already be negative values, so it can't be in the correct domain. So there's no other points. I want to go through a little bit for next exercise, and tomorrow we can focus on the question only. Do you have period 1 tomorrow? No, not period 1? Oh, we don't have tomorrow. Well, okay. So I'll go through some of this and you can think about that and we can do it on Wednesday. Okay, we can do the questions on Wednesday. So when is a function differentiable? Okay, important. Someone keep talking for a whole lesson now. Please stop. Okay, it's very important. Okay, it's very, very important. That's the most important exercise in this chapter. So when is a function differentiable? Okay, so first of all, let's think about differentiable. As I tell you, there are a couple of things we're talking about. Okay, so what we have talked about? We have talked about defined limit exists, and we talk about continuity, let's say continuous, and then differentiable. Okay, we talk about those 4 things. Okay, those 4 things is the general review from the whole chapter. We think about those 4 things for a single point. Okay, so what I can tell you is define a limit. There's no interactions between each other. It can be defined but not limit exists. It can be limit exists but not defined, but it can both exist and both not exist. Okay, there's no influence between each other. But those 2 things will affect the continuity. If one of defined or limit is across, it definitely cannot be continuous. Okay, if it is not defined, it can't be continuous. If the limit doesn't exist for that point, it cannot be continuous for sure. We don't need to think about the next stage. Okay, I can say that stage 1, stage 2, and stage 3. If I have failed in stage 1, not successful in stage 1, I don't need to think about stage 2 and stage 3. They must be failed for sure. Okay, must fail for sure if the stage 1 is not satisfied. If stage 2 satisfied, okay, if something is defined and limit exists, okay, do you know something? If it's defined and its limit exists, but it can not necessary to be continuous. For example, the case I show you, the really extreme case. At the point 1, limit exists. Okay, limit exists. The limit is actually let's say 2. The limit is 2. But it is defined. It defined f1 equals to 4. But they are not equivalent. Therefore, it's not continuous, even though it is defined and limit exists. But it's not continuous. Okay, if something is not continuous already, if it's not continuous already, it can't be differentiable for sure. Okay, if not satisfied stage 2, don't need to think about stage 3, not be differentiable for sure. So it must be, okay, now you start to think about what kind of points can be differentiable. Then it must satisfy that it's continuous. Okay, it must be a continuous graph. Then we start to think about whether it's differentiable or not. If it's not continuous, you don't need to think about the differentiability. No, for sure. Okay, so that's the first thing I want to talk about. So in general, a function is not differentiable at x equals to a if the function of the graph is not continuous at a. Okay, the first case is not continuous at a. When it's not continuous, when there's a vertical jump, when there's a horizontal jump, or when this is a vertical tangent at that point, they are not continuous points. Okay. Actually, the vertical, this one shouldn't belongs to here. It should belong to the next dot point. Okay, so it's not continuous when there's a vertical jump. It's not continuous when there's a horizontal jump. I give some examples to that. When there's a vertical jump, I can say the graph looks like that. It's a vertical jump. If it's a horizontal jump, the graph looks like that. There's no values in between those 2 points. It's a horizontal jump. Okay. Number 2. Has a sharp point or cusp at x equals to a sudden change in directions. Okay, a sudden change in directions. Like that. Okay, a sudden change in directions looks like that. Or has a vertical tangent. Has a vertical tangent at x equals to a. So what the graph looks like. Do you know what graph is that? Do you know what graph, like what kind of function is that? I can say that's x to the power of 2 on 3. Remember what we learned for the power functions? We have even or odd. Then we will have graph in the first and second quadrant. But because the power is smaller than 0, it will increase slowly in that shape. If we have that, that is a vertical tangent at x equals to 0. Then at that point, x equals to 0 is not differentiable. It's not differentiable. If I want to make a general point, okay, if I make something in general, I can say, you must write this down, okay? For fx equals to x to the power of n, where n is smaller than 1. F dash 0 does not exist. F dash 0 is undefined. Let's say f dash 0 is undefined at x equals to 0 is not differentiable. At x equals to 0 is not differentiable. So for any power functions, if the power is less than 1, if the power is less than 1, it can't be differentiable at x equals to 0 for sure. Okay, that's case number 2. Okay, first, if it's not continuous at that point, then it's not differentiable. Second, if it's a sharp point or sudden change, It can't be differentiable even though it's continuous. Okay, can I say that's continuous but it's not differentiable? That's case number 2. Case number 3. Case number 3 is this one. But it's not that. Here. Number 3 is here. Derivatives never exist at endpoints. Okay, if your graph has endpoints, the derivative never exists. Never. Okay? Doesn't matter regardless whether the endpoints are included or excluded. Okay, doesn't matter. If we have a graph looks like this. We have 2 endpoints. One is included and the other one is excluded. Not differentiable. Not differentiable. Doesn't matter if it is included or excluded. Endpoints do not have differentiabilities. Okay? Doesn't matter if it's a closed circle or open circle. Can't differentiate at that 2 points. So when you want to sketch a derivative graph, let's say that's y. If you want to sketch the derivative graph dy dx according to x, let's say we have gradient, increasing gradient, and it's all positive. But it must have 2 open circles here. It's all increasing than 0 and must have 2 open circles at the endpoints. Can't be differentiable at those 2 points. Okay, that's the 3 things. Okay, 3 things. Actually, this one, my notes is not very. I need to change the order. So this dot point is actually belongs to number 1 because the limit doesn't exist means it's not continuous. Okay, it can be included in the case which is not continuous. So you just need to think about 3 things. Is that point continuous? Is that point a sharp point? Is that point an endpoint? Okay, 3 things we need to think about. Whether it's continuous, if it's continuous, whether it's a sharp point or cusp or like a sharp change, whether we have endpoints. That's the 3 things we test which points are not differentiable. Okay, which points are not differentiable. Okay, functions can join. Okay, next thing is function can join if they intersect. Okay, which means they connected. Okay, they are continuous. Can join when they intersect. But they can join smoothly or not smoothly. Okay, let's show when it's joined smoothly. If I want to draw smoothly, let's say we have 1 point here and that's one function. If I want to join smoothly, I can show like that. That point is smooth joined. That's smoothly joined. But we will have something joined not smoothly. For example, we have here and here. Can see it's not smooth, okay? Like sharp change there. So not smoothly. It's not smoothly joined. If it's not smoothly joined, which will give you not differentiable. Okay, Because this is sharp change, it's not drawing smoothly, then it's not differentiable. Drawing smoothly means it's differentiable at that point. Drawing smoothly means it's differentiable at that point. Drawing not smoothly, which means it's not differentiable at that point. Well, the question now comes with when is drawing smoothly, when is not drawing smoothly. I can't really always see by eyes, okay? There needs to be a way like I can test it, whether it's drawing smoothly or not. Okay, how we can test about this. Okay, when I say drawing smoothly, it must mean I have two functions at least, and I want to connect them. Okay, I want to connect them. I have f1x and f2x, I want to connect them to form one function. Where's the connection point can be drawn smoothly or not smoothly? Okay, that's the problem point. Okay, we may occur like can't join or can't join smoothly. It's the same as when we talk about the continuity. Okay, it's always continuous if there's only one function. But when it's not continuous, when I try to connect two functions together. Same as differentiability. We want to connect two functions. First, they need to connect. Second, they need to connect smoothly. The connection point is the point we need to think about, we need to test about. So let's say the example, fx equals to f1x and f2x. For f1x, x belongs to negative infinity to a, not including a. For f2x, I have x belongs to a to infinity. Okay. If f1a equals f2a, which means they intersect, which means it's continuous. Even though this one is an open circle, that one is a closed circle. But they intersect. And the open circle overlap the closed circle, they become the closed circle. That's the first thing it tests about is continuous and it intersects. I know it's a continuous graph now. The second thing I need is drawing smoothly, which I need f-1a and f-2a will be same. The gradient at that point for the left-hand side function and the gradient at that point for the right-hand side function needs to be the same, which means they have the same gradient at the same point, they can join smoothly. Okay, they can join smoothly. So I will give that as differentiable. It tells you it's differentiable at that point. Then the drawing point is smooth. Okay, the drawing point is smooth. If I say drawing smoothly, give me two things. First, the y value at each function at that point will be the same. They join. Second, the gradient at that point for both functions will be the same. They join smoothly. Okay, drawing smoothly is the most important concept we're talking about, and it's also important for yourself. Okay, you need to know what means by drawing smoothly. Okay, drawing smooth means you have intersects, you have y value same, you have differentiability is the same, like gradient the same. Okay, the gradient is the same. Yeah. No, like the open circle, closed circle, that should be the same point. Like yeah, 4-2 is the open circle, 4-2 needs to be the closed circle, then they needs to be the same circle, which means they join together. Otherwise, one open here, closed here, they cannot join. If it's open here, closed here, it's a closed circle in total, like after the overlap. Okay, so if two curves join smoothly, I will highlight here. If two curves join smoothly, first, two things give to you. The curve intersects. Second, the curve at the point of contact are the same for both functions. Okay, the gradient are the same for both functions. I will highlight that. That's the concept. Okay, that's the concept. I will show you one example. Okay, I will show you one example. Let f map R to R fx equals to a hybrid function x and minus x. If x greater than 0 and x smaller than 0, that is fx equals to absolute value. Even though the absolute value is taken out of the cross, you may still want to know what is it. Okay, absolute value means you put any value in, you give you a positive value out. If it's absolute -2, that will give you 2. If you just put a positive value 2 in, that will still give you 2. Okay, every negative become the positive. So let's think about what's the shape of this graph. What's the shape of this graph? That is y equals to x, that is y equals to negative x. That's a point 0, 0 here. Okay, all the other points is continuous and is differentiable for sure because it's like a smooth function. The only problem may be x equals to 0. I need to test about x equals to 0. Okay. Now, first, I will sketch, let's say f1x equals to x, when x greater equals to 0, f2x equals to minus x. Okay, first, I will test about whether they join or not. f10 equals to 0, f20 equals to minus 0, which equals to 0 as well. So f10 equals to f20, they intersect. Okay, which means they are continuous. It's joined and it's continuous. What's the next thing we need to think about? Is the gradient for both functions. f1 dash x equals to 1. f-2x equals to -1 for both functions. Therefore, f-10 equals to 1. f-20 equals to -1. So f1-0 is not equals to f-20. Not smooth. Smoothly joined. Okay, it's not smoothly joined. The gradient for those functions are not the same, which means at that point the gradient are different for both functions. One is for that one and the other one is different. For the same point, but the gradient will be the different for both functions. Then therefore that point cannot be differentiable. It's not differentiable. Okay, it's not differentiable at that point because it's not joined smoothly. So when you talk about the differentiability for fx, I will say is differentiable for x belongs to R except 0. It's differentiable for any other points except the point 0. Okay, except the point 0. And if you want to sketch for the gradient function, must be open circle here. 0, -1, 0, 1. Because they have different gradients, I can't have any of that. I can't take 1, I can't take -1. I don't know which one to take. So I put open circle for both ends. Okay, both function. So red is gradient function. So the red one is the gradient function. So the gradient function will be 1, -1, but at 0 you have open circles for on both equations. Any questions? Okay, if no, I will continue on Wednesday.